Okay, in this new video, we're going to start talking about wellbore stability. And before we start, we're just going to go through an introduction about the wellbore environment. We have seen so far that we can have stresses in the subsurface, like for example, if I were to draw here a representative volume in which I have in situ stresses applied on a mass of rock. Let's say this is at a certain depth, and I have a vertical stress, horizontal stresses, and also I have at in a pore pressure, so that I have effective stresses. This is going to be into a rock that is going to have its own elastic properties, let's say Young modulus, Poisson ratio, and failure properties like UCS and a friction angle. Okay, uh, if we drill a wellbore into a place, these are variables that we cannot change. They're already to begin with. And when we drill a wellbore, like for example, the wellbore I'm drawing in this case, one more try. Okay, that's a little bit better. Let's say that we have a wellbore that at some point it deviates. What we want to know is if we're going to be able to drill such wellbore and it's going to be stable or not. And in addition to the in situ variables like the in situ stresses, the orientation, pore pressure, and the properties of the rock, we're going to have other variables that are part of the wellbore. And probably the most important one is going to be what is the mud pressure when that wellbore is being drilled. And also is going to be important what is the mud composition, the mud fluid chemistry, and also very important is going to be the wellbore orientation, whether this wellbore is vertical, horizontal, or it's inclined at some location. So let's try to understand what those variables are. And as I was telling before, the most important one is going to be the wellbore pressure. The wellbore pressure is going to be given by in this simplified equation by the hydrostatic column, which is the result of the weight of the mud inside the wellbore times the particular depth, true vertical depth that we are considering. So in this sketch, you can see very well that for a given depth, we may have a pore pressure in the rock, a vertical stress in the rock, total stress, and somewhere in between, we're going to have our wellbore pressure. The wellbore pressure is going to be controlled by the gradient of pressure, and that's going to be controlled by the weight of the mud. In conditions in which the wellbore pressure is higher than the pore pressure, then that density of the mud has to be in between the density of the water, if it's under hydrostatic condition, and the density of the rock. In this case, notice that these numbers are in pounds per gallon, which is the usual unit for the pressure gradient in drilling. All right, so the pressure of the wellbore is going to be very important because we are going to use this pressure in the wellbore to our advantage in order to improve wellbore stability into in some cases. This is what is called overbalance drilling. As, as we're going to see, that's going to affect what are the stresses around the wellbore. And as I just told you, Two is going to be very important in many cases to improve wellbore stability. For example, if you were to drill a wellbore in sand without any cohesion, any cementation, that would be impossible without the help of the drilling mud and the formation of a mud cake that's going to help us to obtain this additional stress, which is going to make this wellbore stable. If we were to drill in conditions in which the wellbore pressure is lower than the pore pressure, that's something called underbalance drilling, and we're going to see that also that might be useful in some other cases. But before we jump into looking at the stresses around the wellbore, let's see what is the effect of a mud cake and why this overbalance drilling is important. Whenever we have a pressure in the wellbore, in the mud in the wellbore, which is higher than the pore pressure, and if our mud is developed in a way that it has particles that can clog as they get into the rock, this is going to form what is called a filter cake, formed by the filtration of particles trying to get into the rock because there is a pressure difference. If there is a pressure difference, there's going to be a flow from the mud into the rock, and some of these particles are going to get entrained as they try to get into the rock. And as they do, they're going to filter out and they're going to form this mud cake. And this mud cake is going to be very important because it's going to help us have this difference in pressure between the pressure in the wellbore and the pore pressure in the rock, which is going to act as an effective stress support on the wall of the wellbore. Just imagine for a second that this mud cake or filter cake is fully impermeable. If it will be fully impermeable, then we could have a very well-defined difference between the pressure on this side, on the wellbore, and the pressure in the pores in the rock, because there is an impermeable barrier. Well, with the mud cake, it's something similar, but it's not impermeable. It has some permeability, but it is low enough so that it is possible to have, in a reasonable distance, a difference in pressure that acts similar to what we have as a membrane, adding an effective stress support on the wall of the wellbore. And say, in other words, this filter cake, whenever we have a pressure in the wellbore which is higher than the pore pressure, is going to push against the wall of the wellbore, and as we're going to see later, this is going to allow us to drill stable wellbores in some locations. Okay, so what we're going to do now is we're going to use the equations that we have learned before from linear elasticity in order to determine what is the state of stress around the wall of the wellbore. Like, for example, somewhere over here, we want to know if, because of drilling a wellbore now, the state of stresses might change, and if it change, how much it changed, and if the rock approximated failure. Because if, because of drilling the wellbore now, we have failure of the rock, we have to take that into account into wellbore stability. And that's what is going to, or what we're going to use in order to predict that the wellbore is stable or not. Let me go a little bit further. I'm going to add some variables over here that we're going to see in just a bit what they are. This is going to be the vertical stress for a vertical wellbore. This is going to be the radial stress, and this is something which is called the hoop stress. All right, so as you notice, these wellbores are circular. The cross section is circular, and because of that, we're going to use equations of stresses that correspond to a cylindrical coordinate system. And these equations are going to involve stress variables that are not going to be like we had before, for example, sigma xx, sigma yy, sigma zz. Notice that now our coordinate system involves an angle and also involves a radius. And this is the angle theta and the radius r. When we consider a element in this cylindrical coordinate system, now our normal stresses are going to be sigma rr perpendicular to the face, which is perpendicular to the radius, sigma theta theta, which is the stress perpendicular to the face, which is perpendicular to the direction in which theta is varying, and sigma zc, which is parallel to the z-axis, which is similar to what we have seen before. So the two ones that change are sigma rr and sigma theta theta. Notice that the shear stresses also change. Now we have sigma theta theta z, for example, in this case, sigma theta r, and for example here, this one will be sigma z theta and sigma zr. I don't want you to get into a lot of detail about what these stresses are, what their convention is, because we're not going to use that much. What we're going to do is we're going to utilize this notation to predict what are the stresses around the wellbore and whether if those stresses get to failure or not. So the important part from this section is to know that we're using stresses in a cylindrical coordinate system, and now our normal stresses are sigma rr, sigma theta theta, and sigma zz. Particularly, we're going to use quite a bit sigma rr and sigma theta theta, because those are going to vary as you go around the wellbore, as theta varies from 0 to 360 degrees. Okay, so how do we solve now for the stresses, all these stresses around the wellbore for a given stress condition in 3 dimensions? The solution is not easy, but we are lucky that we have someone who already solved this for us and found the equations for it. And this someone is Mr. Kirsch, who worked on this problem and found the solutions for this problem. And these are the equations for a vertical wellbore. And you can see they are a little bit long, but we're going to explain step by step what are the components of this equation. This is not something that I would recommend that you memorize, but you should know what is the influence of each of these parameters on the solution. So how did Kirsch found this solution? What he did was to solve this equation that we have seen before, and he solved this analytically for a circular cavity in an infinite medium, which is isotropic, it is elastic, and is homogeneous. By having those assumptions, he solved for stresses around the wellbore at a given distance from the wellbore r, and for a given angle with respect to one of the horizontal stresses, and all around the wellbore for this homogeneous and linear elastic solid. So we're not going to go again into the details how Kirsch found this solution, but we're just going to use it, and for now I'm just going to explain what of each of these parameters mean. Okay, so let's go to the first term. The first term, it captures what is the influence of the stress on the wall of the wellbore. If you notice, this is the difference between the wellbore pressure and the pore pressure. And as we were saying before, this is going to have a direct influence on what are the stresses around the wellbore. So let's see first what would be the influence of this stress, and this is going to be right here. And let me expand this window a little bit. You can imagine that if we have a solid without, let's forget a minute now about all the far field stresses, the pore pressure. Let's imagine that we have an impermeable rock and inside we have a pressure in the wellbore. If you increase the pressure in this wellbore, what you're going to cause is that in radial direction, in tangential direction perpendicular to the radius, what you're going to cause if you increase the pressure in the wellbore is an extension of this diameter, and that's going to result in tension. And perpendicular to this tangential direction, we're going to have the radial component, and the radial component is going to be equal to the pressure applied on the wellbore of the wall. So for a pressure in the wellbore different than zero, the result is that all around the wellbore, we're going to have a radial stress, which is in the direction of the radius, which is going to be positive and equal to the pressure in the wellbore, and a tangential stress, which is sigma theta theta, also known as the hoop stress, which is going to be negative and is going to be in tension all around the wellbore because of what we were saying before, that this is going to extend. It's straightforward to see that the pressure in the wellbore is going to be, the radial stress is going to be the pressure in the wellbore, but it's not that straightforward to see why this is equal to the negative of the pressure in the wellbore. That's part of the solution from Kirsch. So we're not going to go into details about to explain why that's the case. Something very important to notice also from this solution is that these stresses are going to fade as you go further and further away from the wellbore. So as the radius r increases, these stresses in the far field are going to decrease. The radial stress is going to be less compressive, and the hoop stress is going to be less tensile as you go further away. And more or less at the distance of about 2 radii from the wall of the wellbore, so that will be 1 radii, 2 radii from the wall of the wellbore, we already see that that decrease is quite important. Okay, so here we capture what is the effect of increasing the pressure in the wellbore. If we consider the effect of the pore pressure, the only thing that we have to do is to consider that the effective stress or the effective support that we're going to have on the wall of the wellbore is the pressure in the wellbore minus the pore pressure. And when we do that, what we end up with is with this term that tell us what is the radial stress and the hoop stress as a function of the radius, and we know that this is not going to be influenced by the angle theta, so there is no component of theta. All right, let's see now what is going to be the influence of the far field stresses. And there are going to be two components for this case. One is going to be the isotropic component. Notice that in these two equations, this one is the same. It's just the average of the far field stresses. And there is going to be an anisotropic component, which is going to be different either for the radial stress or for the hoop stress. So let's start for the isotropic component. The isotropic component is right here. And if we use the Kirsch equation, we're going to obtain that because of the application of a far field stress, which is the same in all directions, and in this case I call it sigma infinity, and because it's the same in all directions, we can tell it's isotropic. What this is going to cause around the wellbore is going to be a compression in the hoop stress or the tangential stress all around the wellbore. And because in this case, I'm going to assume that I have no wellbore pressure at all, no radial support, the radial stress at the wellbore is going to be equal to 0. And this is what we see in this equation and this plot over here, that the radial stress all around the wellbore from theta that goes from 0 to 360 is 0 because I have no radial support, and the hoop stress is going to be positive and it's going to be a compression and it's going to be the same going from 0 to 360, and it's going to be equal to 2 times sigma infinity, or the far field stress. So let me explain why this is the case, why we have a compression in this uh, in this oh, let me change this, in this particular scenario. And I'm going to make a drawing about this. Let's just consider for now a two-dimensional section, which is going to be just half of the problem that we are observing. If we have stresses in all directions, what is going to happen is that, let me move this a little bit more over there, okay. All right, if we have these stresses sigma infinity in all directions, what Kirsch predicts is that I'm going to have a compression in the hoop direction along this cavity. And this is similar to what you may observe in those bridges made out of rock, right? In which, if we choose just this section which is closer to the cavity, what you would expect is that you could make here a bridge, and this bridge would not fall because this hoop stress sigma theta theta is positive and is equal to, according to the Kirsch solution, to 2 times sigma infinity in compression because of the shape of this cavity. And if we go to the equations, the equation is similar to what we saw before, and is going to, the influence of the cavity is going to decrease as you go further away from the center or from the wall of the wellbore. So we know that if we have a far field stress which is different than 0, then this is going to cause hoop stresses and radial stresses that are going to vary depending on where you are in, and especially about the distance between the center of the wellbore and the particular position in which you are. So if we take these equations now into the Kirsch equation, sigma infinity here will be the average stress, and it is this stress over here. This average stress is the one which is going to be the second term. And the last term is going to capture whenever we have stresses which are different in perpendicular directions. So let's say now that our maximum horizontal stress is different than our minimum horizontal stress for this wellbore. The way we're going to capture that, the difference between those two, is going to be through this additional stress delta sigma, which is going to be aligned with the direction of the maximum principal stress that we're considering in each case. So for this particular case, what I'm assuming is that, similar to what you see on the left, we have a cavity, and in this cavity I have sigma H max in this direction, and sigma H min in this other direction. So what I'm doing is I'm just dividing the problem in two. One component is the isotropic component that we already solved, and the other component is going to be the additional stress I have because SH max is larger than SH min. So when that's the case, then what I'm going to do is I'm just going to solve this problem for the case in which I'm going to do what I have on the left, and is to consider that there is no stress on the direction of SH min in this case, and we do have stress in the direction of SH max, and this is going to be delta sigma, where this is a cavity. And now, as you may expect, there is going to be a difference whether we have an element which is in this location or in that location. And that's going to be given by this angle theta. And this angle theta is going to be defined between the particular point I'm looking at and the direction of delta sigma, or in general, for a vertical wellbore, the direction of SH max. So remember, this is something important. This angle theta is going to be measured from the direction of the maximum stress in the plane perpendicular to your wellbore towards the particular point that you are considering. So here we have the result of the Kirsch equation, and what we see is that the radial stress, because we don't have in this case any pressure in the wellbore, we're considering that through another equation. Pressure in the wellbore is 0, and therefore the radial stress is 0, and all around the wellbore is 0, from 0 to 260 degrees. But look at the hoop stress. The hoop stress here in green, it's varying, and it varies actually like a sinusoidal, or in this case a cosine equation. And for theta equal to 0, which is going to be this point, and it's going to be an element right here, is going to be a tension. And for theta equal to 90 degrees, it's going to be a point over here or something over here, is going to be a compression. And as you vary the angle theta, and you continue going through here and through there, this hoop stress is going to go up and down. Let me explain why this is the case. Okay, so I'm going to use here the notes, and what is happening over here is the following. I have a cavity in the center, and I have a stress that it's applied in this direction. This stress has to travel through the rock, and as travels through the rock, this stress is going to have to go through the cavity. And going through the cavity, the stresses cannot go through this empty space of the wellbore, and therefore are going to have to go around it. So a compression stress that was traveling in this flow line that before was going straight, now it's going to have to bend. And the same for this stress, where this is a compression streamline. Let me improve these arrows. This is a compression. These compression streamlines, as they get closer to the cavity, they're going to have to bend. As you get further away from the cavity, they're going to have to bend less and less. And as you are quite far from the cavity, the solid is not going to feel almost any stress at all. So if I were to pick an element of rock somewhere over here, I know that the stress in this direction, the compression, is going following these lines. And let's see what it would happen, for example, at a location equal to 90. Let me move this a little bit to the left. So we're looking at the point right here, and what Kirsch is telling me that this should be a compression. And this kind of makes sense with what we are drawing here, because the result of these lines, of compression lines bending around the cavity, is that at this place, I'm going to have a compression, and because these lines are gonna have to get closer and closer to each other, all the stress that before was going through directly to the cavity, now I cannot go through the cavity anymore, but it's going to concentrate here. So the stress that I'm going to have in this case, sigma theta theta, is going to be a compression in the radial direction. And not only that, but it's also going to be quite a bit higher than the stress in the far field, because all these lines are getting closer and closer to each other, and all this rock has to now carry the stress that this rock over here is not carrying anymore, because now I have a cavity. That's why we have a compression at this point, which is this location. And let's see now what is the case of the tension. For the tension lines, what is happening in this case is that as we get closer to this point, this stress, which is a compression, let me do it with another color. Is going to have to decompose in two directions. So if we decompose this stress vectorially, the result is that there's going to be a component that is going to push into this direction, but there is going to be also a component that is going to go down in this case and up in this other case. And the result of that is that for a particular element located at theta equal to 0, what I'm going to have is a tension. And it is because the presence of the cavity and the orientation of where I am with respect to the orientation of the stress that I'm going to have either a tension at this point and at that point, which are this and that, or a compression, which is this peak, at this point or that point. So if we continue with this point, these are the 2 points of compression, 90 and 270, and these are the 2 points of tension, which are 0 and 180. And here you can see also the solution for Kirsch that tells you that the compression at this point is going to be equal to 3 times this magnitude delta sigma. So that means if I apply delta sigma in this case, here at the wall of the wellbore, I'm going to have 3 delta sigmas. That's something which is called stress amplification. And as we're going to see later, this is particularly important for fractures. And in the case of fractures, we're going to talk about stress intensification and how much as the stress increases compared to when we have a cavity or when we have a fracture is going to be very important. In this case, this stress intensification is equal to 3 because we apply 1 delta sigma, but we got 3 delta sigma over here, so the ratio of that is 3. Okay, well, the question to predict this line is going to depend on the angle theta, on the radius. If you go further away, not at the wall of the wellbore, but a little bit further away, now the radial stress also is not going to be 0 anymore, but it's going to be a different value than 0. And here you have the equation. And also now we have the equation for the shear, because there is going to be also a shear associated with these stresses and this deviatoric loading. Finally, we put all of that together and we get the Kirsch equations that summarize the 3 actions: the effective radial support, the far field stress, and the additional component of the far field stress, which, as you can see in this case, this one is affected by the angle and depends on the position of the rock with respect to the direction of the applied stress. Okay, so with these equations, now we are able to calculate what is the state of stress around the rock. Here we have one example, and it's also, this is a computation for radii, which is not just at the wall of the wellbore, but a little bit further away. Let's see, in this case, we're not considering the effect of the wellbore pressure. There are just far field stresses. And here we have the result of what will be the radial stress. The radial stress, as we get, for example, into this wall, it has to be at this particular location. This is going to be the radial stress in this direction. And that's going to have to be 12 MPa. If we go to the color bar over here, we see that that makes sense. 12 MPa is somewhere over here. Radial stress at a location somewhere over here is going to be 3 MPa, and that makes sense with what we see in this location. At the wall of the wellbore, since in this particular case I don't have any effective radial stress support, that's going to be 0. So all around the wellbore, radial stress is 0, and that's a value that corresponds with 0. Let's now take a look at the hoop stress. The hoop stress next to the wellbore is going to be here quite high. You see it reaches the value of more or less close to 30, because this is the region top and down in this plot which coincide with the points in which I would expect the maximum compressive stress, because the direction of the maximum stress in this case is going here horizontally. So if this is direction of the maximum stress, then these are the points where the maximum compression is going to be. And perpendicular to that, I'm going to find the points of the lowest stress, hoop stress. And that's going to be, in this case, it reaches, if I remember correctly, more or less a value close to negative 3 MPa, which is the value that we see in colors over here. And I did one more thing over here. I converted those values of radial stress and hoop stress to principal stresses, just to see a little bit better the principal stresses. In this case, we see the value of the principal stress sigma 3, the least principal stress, that goes in lowest value. It's close to the wellbore in these locations, here and there, which is about -3. And the maximum stress, which will be compression, is located over here, where its maximum value is about 30. All right. In the homework, you're going to do a problem similar to this one, but just for a given radius and a given angle theta. In the next lecture, what we're going to do is we're going to use these equations in order to predict when we're going to have failure around the wellbore. And we're going to use the equations that we have already used to predict failure, and those are going to be particularly tensile failure and shear failure. Tensile failure is going to be related to the minimum principal stress, and shear failure is going to be related to these two, sigma 3 and sigma 1. All right, so that's for the next lecture.